Okay, so this is the first BioNMR core workshop, and our topic is 1D and 2D AMR methods for small molecules. And I'm Minli Xing. I'm the senior lab specialist in the BioNMR core. First, I'll introduce the BioNMR core staff to you. So Deb, I'm sure most of you have met Deb before. He's the director of our core lab. He's mainly responsible for the 800 and 600 in the chemistry building. And I joined the lab 2 years ago as a senior lab specialist. I'm mainly responsible for the 600 and 400 in Mary Sue Coleman Hall that are mainly used for small molecule characterization. And Emily is our faculty director, and Kathy is the director of operations. I have our contact information here. So after the workshop, if you want to run any new NMR experiments, or if you want to get trained on any of the instruments, feel free to contact me or Deb, and we can set up an account for you so you can run those AMR experiments. And this is a list of the BioNMR core workshop topics that we want to cover. We will start with this 1D and 2D AMR methods for small molecules today. And our plan is to do this workshop quarterly. So in another 3 months, probably in November, we will do another workshop on protein backbone dynamics, followed by protein backbone assignments, diffusion NMR, methyl NMR strategies for large proteins, and NMR approaches to probe intrinsically disordered proteins, sex NMR, relaxation dispersion NMR, RDC, and metabolomics, and so on. And there might be other topics that you are interested in, so feel free to send us an email. I have our email address listed here, and we can definitely add those topics into our workshop list. And we are planning to do this workshop long-term in the following 1 or 2 years. So it's never late to let us know the topic that you are interested in. And for today's workshop, so for those of you who attend the workshop today, you will qualify for 24 hours free instrument time on the 600 megahertz AMR in Mary Sue Coleman Hall. And you can use this free instrument time to run any AMR experiments, and you can use those time at once or separately. And Deb and I will keep track of your usage, so we'll make sure that you will not get billed for those 24 hours. And this free instrument time will expire in 3 months on November 1st. And so this is a very good opportunity for you to use those free instrument time to run new AMR experiments to characterize your small molecules. Okay, now we'll move on to the topic of the workshop today, 1D and 2D AMR methods for small molecules. And here is an overview of what will be covered in today's workshop. And I will start by introducing the AMR instruments to you. So we have 5 AMR instruments. I'll give the properties of the instruments one by one. So later on, when you have a compound, you will know which instrument is best to choose for your compound. And then I'll give some tips on sample preparation. And the major part of the workshop will focus on the AMR experiments. We will go through the 1D and 2D AMR experiments available one by one, and then you will know which AMR experiment for your compound is best. And then we will set up some of the experiments on ICON-NMR. And after that, if we have some time left, I will cover data processing and analysis by the software called MNOVA. So we have a total of 5 instruments. In chemistry building, we have 3. The first one is this 800 megahertz, and this one is located in 1047 chemistry. This one, similar, maybe you have used other AMR instruments before. Similar to those, it has a 24 sample case that can automatically load samples and inject samples. And it has a Bruker-New console, so it is capable of running many of the modern and advanced AMR experiments. And this instrument has a 5mm triple resonance inverse detection probe with automatic tuning and matching. So it has a 5mm probe, meaning that you can use any 5mm AMR tube in this instrument. Triple resonance means it can detect proton, carbon-13, and nitrogen-15. Inverse detection indicates that the inverse coil of the probe is proton, so it has higher sensitivity for proton. This one has a cryo probe that is cooled by liquid helium, which provides a 4-fold increase in signal to noise ratio, and also it has automatic tuning and matching. And in the same room, we have another 600. We just upgraded this 600 to Bruker last year. This one has more sample precision. In the sample case, this one can hold 64 samples. Also has a Bruker Neo console and a similar probe as the 800. So both the 600 and 800 in 1047 are used for protein NMR experiments. And on the second floor of the chemistry building, we have another relatively old NMR instrument. This one is a 600 megahertz. It has an old Bruker console. It's called Advanced console. So compared with the Neo console, it's relatively old. And this one also has 5mm triple resonance inverse probe. However, only the proton channel is cooled by liquid helium. So for carbon-13 and nitrogen-15, this one will have lower sensitivity. And in the Mary Sue Coleman Hall, we have two AMR instruments, and those are mainly used for small molecule characterization. This first one is a 600 megahertz with Prodigy probe. This one was just upgraded to Bruker last year. And we added 24 sample case and a Bruker Neo console. And the probe is different from the ones in the chemistry building. It has a liquid nitrogen chilled Prodigy probe with automatic tuning and matching. So this Prodigy probe is cooled by liquid nitrogen that provides twofold increase in sensitivity. And this has a broadband probe. So the inner coil of the probe is now X nuclei. So it is capable of detecting X nuclei. And it also can detect proton and fluorine. And in the same room, we have a 400 AMR. This one is still varying. It's not upgraded to Bruker yet. It has a very console and a 5mm proton fluorine X inverse probe. So this table summarizes the properties of those instruments. So I compared those 5 instruments that are available in our core lab. We can compare their magnetic field, how the probe is cooled, how the probe is designed, and the nuclei detected. So of course, the 400 has the lowest magnetic field and the 800 has the highest. And the probe is cooled by different methods. The 400 is just a room temperature probe. It's not cooled at all. And the 600 has a liquid nitrogen cooled probe. And our other 3 in the chemistry building are all liquid helium cooled probes. And the design of the probe is different. So the 400 has an inverse probe that can detect proton and fluorine in the inner coil, and the outer coil is X nuclei. And the 600 has a broadband probe with the inner coil being X nuclei, while the other 3 in the chemistry building all have an inverse probe with the inner coil being protons. So the nuclei detected are also different for those 5 instruments. Both the 400 and 600 are capable of detecting proton, fluorine, and X nuclei. And the other 3 in the chemistry building are capable of detecting proton, carbon-13, and nitrogen-15. So those in the chemistry building, those are mainly used for protein NMR experiments. And for the ones in Mary Sue Coleman Hall, they are mainly used for a small molecule characterization. Okay. I think we have a suggestion from Emily to turn on the pointer laser. Let me see if I can find that. I'll do that just in a minute, right? Okay, so the table, the properties we summarized for the instrument properties will have an effect on the instrument sensitivity. So for every 100 megahertz increase in the field will result in 20% increase in signal to noise ratio. So from the 400 to 800, you will see dramatic increase in sensitivity. And then the liquid nitrogen cooled probe will provide twofold increase in signal to noise ratio. Liquid helium cooled probe will provide a fourfold increase in signal to noise ratio. And also the inner coil of the probe nuclei will have higher sensitivity. So those sensitivity rate will have an effect on the experiment time. We can just compare those 4 instruments. I did not include the one in the second floor of the chemistry building. So I compare the 400 in Marysville Common Hall, 600 in the Marysville Common Hall, and the 2 instruments in Chem 1047. So we can just use some standard sample. For proton, we can use 0.1% ethylbenzene. For carbon-13, we can use 40% p-dioxane just to test the signal-to-noise ratio on those different instruments. So as you can see that the 400 has a lowest signal-to-noise ratio for both proton and carbon-13, and 800 has the highest signal-to-noise ratio. And if you look at the carbon-13 signal-to-noise ratio, the 600 in Marysville Common Hall and the 600 and 800 in chemistry, they are actually quite close. That's because of the design of the probe is different, but those are relatively close to each other. And assuming you want to run a proton NMR experiment on the 400, and that took you 4 hours to get a very good data. And on the 600 in Marysville Common Hall, then it will only take you 10 minutes because of its high sensitivity in proton. On the 600 in chemistry, that's even shorter. That's only 40 seconds. On the 800, it's only 26 seconds. Similar to the experiments on carbon-13, a 4-hour carbon-13 experiment on the 400 will take only 6 minutes on the 600 in Marysville Common Hall, and about 5.5 minutes on the 600 in 1047, and 2.5 minutes on the 800 in Chem 1047. So based on this table, you may make the conclusion that I will just run whatever experiment on the 800 in chemistry. So it really depends on what you need. So if you want to detect X nuclei like boron, nitrogen, or phosphorus, I will go to the 600 in Marysville Common Hall, because the other 600 and 800 in chemistry, they do not have the capability of detecting X nuclei. And if the sample amount is not a limitation, say if you can dissolve like 15 or 10 milligram of sample in your tube, then just run a proton carbon-13 experiment on the 400, you can still get very good data in a relatively short time period. And keep in mind also that the hourly rate of those instruments are different. The 800 is the most expensive one to use. So if you have a very low concentration sample, of course, we'll try first on the 600, and then if not good, then we'll go to the 800. Okay, so now let's move on to sample preparation. These are some tips that I gave based on the questions many users asked me before. For the sample amount for small molecules, I generally recommend 5 to 20 milligram of sample if your sample molecular weight is less than 800. If you have very small sample amount, for example, less than 1 milligram, then just directly go to those higher fields with cryoprobe. So I will start with the 600 in Marysville Common Hall first. And then if that one does not give you very good proton data, then I'll go to the 600 and 800 in chemistry building. And for sample solubility, the sample must be sufficiently soluble to yield an NMR spectrum in reasonable time periods. So check your sample and see if it precipitates out. If it does not dissolve very well, your sample concentration will still be low, and you won't get good data in a short time. And for solvent, of course, you want to use deuterated solvent to avoid large solvent peak and for field lock. So commonly used the ones for small molecules are chloroform, methanol, and DMSO-D6. We use 5 millimeter probe, and so usually the most commonly used ones are 5 millimeter tube that can hold 500 to 600 microliter sample. Sometimes I find users add too much samples to their AMR tube. They even add the solvent all the way to the top of the AMR tube. These are actually not good. So first, it's a waste of your solvent, and also it will dilute your sample because your sample concentration is diluted by the excess solvent. And also it can lead to shimming problem. Those ones with too much solvent will actually have temperature gradient. So the top of your sample and the bottom of your sample will have different temperature when it's inserted into the probe, and that can cause shimming problem. And for a sample AMR tube, 5 millimeter is the most commonly used one. As I mentioned before, you can add 500 to 600 microliter of sample into it. And sometimes you may have small amount of sample, so you want to add less solvent, and so you want to not dilute your sample. So in this case, you can either use a 3 millimeter tube or a Shigemi tube. But for those 3 millimeter tubes, keep in mind that they are designed for 3 millimeter probe. So even though they can be used on our 5 millimeter probe, you can suffer from small loss in sensitivity due to filling factor. So for those kind of sample, I actually recommend those Shigemi tubes. They can hold 300 microliter of sample, and they can still get very good shimming, and you will not have any loss in sensitivity. So these are how these tubes look like. A 5 millimeter one is the most commonly used one. I'm sure most of you have used it before. And those 3 millimeter ones are a little bit thinner, and the diameter is just a 3 millimeter. And this is a Shigemi tube. So for those Shigemi tube, they have a top glass and bottom glass part. So this glass part actually matches your solvent. So you can purchase different Shigemi tubes designed for chloroform, DMSO, or D2O. And for your sample, it's actually those blue part in the center. So you just need to add 300 microliter. And once you add that, since the top and bottom part of your tube, those glass parts still matches the solvent property, you will not have any problem in shimming. So you will still have good shimming and good line shape and good sensitivity by using those Shigemi tubes. And for other sample preparation tips, do not use scratched or warped tubes. And also mix your sample well. Precipitant and air bubbles will lead to bad shimming. And so you can filter sample if necessary. So when you run a sample, if on the AMR instrument, if you notice that the shim is failed, you might want to check if you have a scratch tube or if your sample precipitate or have air bubble. Okay, so now we will move on to the AMR experiments. So we will start with the 1D AMR experiments. The ones I will cover is just 1D proton, 1D proton with solvent suppression, carbon 13 experiments, and some X nuclei experiments. Those are just very commonly used 1D X nuclei. The example I will give is for nitrogen 15 and phosphorus. And finally, I will cover some for variable temperature experiments. So this is just a very common 1D AMR spectrum. I took a standard sample ethylbenzene and I just run a 1D proton. From those 1D proton experiments, you can get very useful data like the chemical shift, the integration, and the coupling constant. So this usually is the first experiment you will run when you have a small molecule you want to characterize. And if the 1D proton data look good, you can go ahead and run other experiments. And one other experiment is those solvent suppression experiment. For example, in this case, I have a sample which is 2 millimeter sucrose that is dissolved in water. If I just run a simple 1D proton experiment without any solvent suppression, I will just see this huge water peak. And this spectrum is actually dominated by this water resonance. And those other smaller peaks from the sucrose peak, actually, I could not see just from those spectrum. And in this case, you will want to run a experiment called proton with solvent suppression. We can actually suppress the water peak. Here, as you see, this peak at 4.7 ppm is suppressed. And once it's suppressed, this huge water peak will not dominate your spectrum. And now you start to see those smaller peaks that is actually from the sucrose sample. So this will be very useful if you have a huge solvent peak. And there are other solvent suppression experiments available to. This one example given here is for multiple solvent suppression. So if you have more than 2 or 3 solvents you want to suppress, we can also run those experiments. And like in this example, the top experiment is one without any solvent suppression. I see 2 huge peaks, and then I want to suppress them. So I can then run a multiple solvent suppression experiment, and then it will selectively suppress these 2 solvent peaks, which is marked by those arrows. And then in this lower experiment, you see that those 2 peaks are gone, and now you can observe those smaller peaks from your compound. So these experiments are actually very helpful. Sometimes when you have, for example, DMSO, and DMSO can absorb water easily. So in your spectrum, you might have a huge water peak and also huge DMSO peak. Then you can choose this method to suppress both of them, and so you won't have those large solvent peaks. So for the proton experiments, once you are happy with that, we can then go to the carbon-13 experiments. And the most commonly run carbon-13 experiments are the carbon-13 with proton decoupling. Here, those CPD is just a method for decoupled proton. So in your 1D carbon spectrum, you will just see a singlet for each of your carbon nuclei. And then we also have a carbon-13 experiment called carbon-13 depth 135. This one is actually also very helpful for you to identify different types of carbon-13 carbon-13 nuclei. So here in this example, on the first spectrum, I just have a regular 1D carbon-13 experiment, and for each of those carbon, it will show 1 peak in the NMR spectrum. And then I can run a carbon-13 depth 135 experiment, which is the second one at the bottom. And so in this kind of spectrum, all those CH and CH3 group will be positive, and the CH2 group will be negative. So indicated by the arrow here, actually the CH2 group from the methylene carbon and in this ethylbenzene molecule. So as you see that this peak is negative in this depth 135 experiment. So this kind of experiments will be helpful to group your carbon-13 nuclei into different types of groups into CH and CH3, and the other part into CH2. Okay, we can also run other nuclei. Like given here is a 1D nitrogen 50 experiment. It's actually very easy, like running your 1D carbon and 1D proton, just a simple 1D experiment. And each of those nitrogen nucleus will show 1 peak in your 1D nitrogen NMR spectrum. You can also run some other nuclei like phosphorus. This one has 1 phosphorus nuclei, and then it showed up in this spectrum with 1 huge peak. And this table is just a list of those nuclei that is, can be detected in the 600 NMR in Marysville Coleman Hall. As I mentioned to you before, this one has a broadband probe, and it is capable of detecting X nuclei. It actually can detect any nuclei with this frequency range from 60 megahertz to 40 megahertz. So it's very powerful. If you have X nuclei you want to detect, most probably this instrument can detect it. This list here is just a sum of those nuclei can be detected. We can also add the ones you want to detect. So feel free to contact us if you have a new nuclei and you want to get a 1D spectrum of that specific nuclei. And when running those X nuclei experiments, many users ask me how to reference those X nuclei. And the traditional way is to do internal or external standard referencing. So you add some standard to your sample, and then you reference that standard to a specific chemical shift. And then you say, okay, my spectrum is internally or externally referenced. And actually now you can use another method called indirect referencing to reference your X nuclei. This method is actually recommended by IUPAC. So it recommends to use a unified chemical shift scale for all nuclei, including proton, fluorine, and X nuclei, be based on the proton resonance of TMS as a primary reference. No internal or external standard is needed. So this is actually based on the frequency ratio of different nuclei. So each of those nuclei, they have this different frequency values. And this frequency value is actually equal to 100 times the frequency of the X nuclei divided the frequency of TMS. So if you run a 1D proton and you get the absolute frequency for the 0 ppm position, get the absolute frequency of the proton of TMS here, and you can actually get it from different software. And then you will put this into the equation and you can calculate the absolute frequency for the 0 ppm position in the X spectrum. So this is very convenient, and if you run any kind of X nuclei, you can easily reference that to TMS. So the software called MNOVA can actually do this for you automatically. Here I will just briefly show you how to do it, and later on when I show you how to process the data by MNOVA, I'll also show you again how to set those indirect references. So the method is that you first add TMS to your sample, and then the concentration of TMS should be less than 1%. If TMS does not dissolve in your solvent, you can add DSS, and DSS can dissolve in buffers such as water or PBS. And then you can just collect a 1D proton and X nuclear spectrum of your sample. And once you have that, you go to MNOVA, open your 1D proton spectrum. So they have those reference tab here, and click on reference. Then you can just set the TMS peak to 0 ppm. And once that is done, you can then go to the X nuclear spectrum. You go to this called absolute reference, and then a pop-up window will show up. It asks you which spectrum you want to reference to the proton spectrum. So you just check the one you want to reference. Here in this case, I checked my carbon-13 NMR experiments, and then just click on OK. Then all of your X nuclei spectrum will automatically get referenced. Okay, so then we'll just cover a little bit on variable temperature experiment. Those are also 1D experiments that you run at different temperatures. For example, if you want to increase the solubility of your sample, you may want to increase the temperature to help your compound to dissolve in your solvent. And for some compounds, you may want to decrease the temperature to help increase the stability. Also, if you are follow low or high temperature reactions, or if you are follow exchange process or conformational changes, you may want to change the temperature of the experiment and see how those peaks in your spectrum changes. Here's an example how the variable temperature experiment can have an effect on your spectrum. So this molecule, it has a piperazzi ring, and this ring, the methylene protons actually can broaden and disappear at lower temperature due to ring inversion. So this ring has axial and equatorial conformational change. As you can see on the spectrum on the right, I can run a experiment at just room temperature, 25 degrees Celsius. And then I just found that those methylene proton peaks are missing, so they are not there. Those smaller peaks is actually DMSO. It's a solvent. So now I slowly increase the temperature. So I increase that to 35 degrees Celsius. And now I see a relatively broad peak over here starts to show up. And if I increase more, now I start to see those methylene proton peaks appear. So as I increase the temperature, the conformational exchange rate also increase. And then you can start to see those peaks in your AMR spectrum. So sometimes if you know that your sample has conformational exchange, it's might worth trying just to change the temperature and see if you have any changes in your spectrum. And on the 600 Emeryville Coleman Hall, we're actually capable of running those variable temperature experiments. For the temperature range of the probe, it can detect any temperature from -40 to 150 degrees Celsius. So the heating is actually done by a probe located at by a heater located at the bottom of the probe. And then the cooling is done by FDS chiller, which cools the air necessary for temperature experiments. And when setting up those cooling, you want to make sure that this FTS chiller is set at least 10 degrees Celsius colder than the desired temperature. And we also need to use special spinner for those experiments. The most commonly one we use those blue spinner that you use for most of the experiments are actually good for 0 to 80 degrees Celsius. And if you want to go to lower or higher temperature, you can use either this KLF NMR spinner or those ceramic spinner. So I would just directly use those ceramic spinner as they can cover the lowest and highest temperature. Those spinners are relatively heavy, and when we use those spinners, we actually need to set up some ejecting air manually. And some other tips are when you set up those experiments, your highest temperature should be at least 10 degrees Celsius below the boiling point of your solvent. And then the lowest temperature should be at least 10 degrees Celsius above the melting point. Listed here are just some of those melting point and boiling point for those commonly used solvents in this table. You can increase or decrease the temperature incrementally by 10 degrees Celsius for about every 5 minutes to let the system to equilibrate. And since we need to set up those temperature manually, and also since we're using different spinner, we need to set up the ejecting air manually. So you need to consult with the BioNMR course staff first. We will sit with you and set up those variable temperature experiment manually. Okay, so now let's move on to setting up those experiments on ICON-NMR. So I'll first describe how we set up those experiments. Then after that, we will have a hands-on session that I will show you on the instrument computer how to set up those experiments. If you haven't run ICON-NMR before, so it's a software that allows you to automatically run those NMR experiments. Once you start ICON-NMR, it will have a list of NMR experiments available to you. So what you need to do is just to select the experiments you want to run, and then click on OK, and it will automatically run for you. So this is just an example of the list of the experiments that are available. And all the experiments I mentioned in the 1D NMR experiments are listed here. And here is a table that gives you the name of the experiments that you can choose on ICON-NMR. If you want to run a 1D proton, just click on the proton 1D experiments on ICON-NMR. And the solvent suppression experiment, we have those N1 available. And we'll also have all those other experiments already set up on ICON-NMR. And also when you select the experiment, ICON-NMR will ask you if you want to change any of the parameters that are specifically for your sample. Some of the important parameters are listed here. Like POS program is actually the most important one, and the BioNMR course staff have already determined the POS program for you. So this POS program determines what types of experiment to run. And other parameters that are available are this TE, sample temperature, and TD is number of raw data points. You can set this to 16K, 32K, or 64K. This number actually determines resolution. If you have a lot of a peak overlap, you may want to increase this value to get better resolution. D1 is a relaxation delay. Usually it's set to 1 to 2 seconds for routine experiments, and there is no need to change it. And the number of scans is actually the parameter that determines your sensitivity. So now the signal to noise ratio is proportional to the square root of number of scans. So if you increase the number of scans, you'll get higher sensitivity. This is especially useful if you have low amount of sample and you want to run a long experiment to get enough sensitivity. O1P is the center of your spectrum, and SW is the spectrum width, and P1 is the 90-degree pulse. So for the pulse program and its P1, and the BioNMR core staff will actually set up those values for you. So that you only need to worry about those other parameters, and you may need to change it depending on your sample condition. And here's the example. So on ICON-NMR, you can actually click on a parameter tab, and then that will open this window that shows you the list of parameters that are available for you to change. The ones that I think is most important are the O1P, 1SW, and NS for those 1D proton AMR experiments. So O1P is determining the center of your spectrum, and 1SW is your spectrum width. And you can actually calculate the spectrum ranges of your spectrum based on O1P and 1SW. So this here is spectral ranges. It will be the O1P plus and minus your spectrum width divided by 2. So for those values I set up here, I can actually calculate the spectral range will be 15.84 to negative 0.884 ppm. So it will cover most of the proton signal. However, if you know that maybe your proton, your spectrum will have a signal at around 16 or 17 ppm, then you can adjust this 1SW parameter. You can increase that value, so it will cover a larger range, so you can see your peak of interest. Also, for number of scans, you can change it. Generally, 32 is good for most of your samples. But if you have a very low concentration sample, you can increase this value. And for different types of AMR experiments, they may have different requirements for the number of scans. For these particular experiments, you can just set the number of scans to any number, so it will be 1 times the integer. So later on, I'll show you that for some experiments, it will require the number of scans to be 8 times the integer. So for the 1D experiment, is relatively simple. Just set it to any whole number, and it will be okay. For the 1D carbon 13 experiments, similarly, you can set up those parameters, O1P and 1SW, depending on the carbon 13 ranges you want to detect. And also the NS number of scans can be set to any values. As you see, because carbon has a much lower sensitivity compared to proton, a normal 1D carbon will need like 10 to 1024 scans, and that will probably take about 15 minutes to accomplish. And this is for the parameters for those depth experiments. It also has those O1P, 1SW that you can modify. And for this experiment, it has some requirements for the number of scans. So you need to set the number of scans to 4 times the integer. And then you can set it up to 256 or 512 and those kind of number. For solvent suppression, if you want to run a solvent suppression to just suppress one solvent peak, select this N water experiment. And then this experiment will actually automatically search for the tallest peak in your spectrum and suppress it. So you must make sure that your tallest peak is your solvent peak. If not, we will have to set up some parameters manually. Just let me know. There are other ways to suppress peaks that are not the tallest peak. And the number of scans will be 8 times N. And O1P and 1SW can also be modified based on your experiment condition, your sample condition. And for multiple solvent suppression, this one is set up to suppress just 2 solvent peaks. So if you do not change any of the parameters, you will find that in your spectrum, the two tallest peak will be suppressed. Also, there are other ways to manually modify some parameters, so it will suppress more peaks. And the number of scans will be set to 8 times N. Okay, so then we will just move on to those 2D AMR experiments. And once I'm done with the 2D AMR experiments, we will go ahead and have a hands-on session on using those ICON-NMR to set up some of the experiments we mentioned in the workshop. So when will you move on to 2D AMR experiments? If you have a small molecule, you get good data in 1D, like a very good 1D proton and carbon-13 experiment, and then you can assign most of the peaks, then there's really no need to run 2D NMR. So 2D NMR are actually designed for complex molecules, and running a 1D proton of your sample. And in your proton spectrum, if you see a lot of peak overlap, like the example I gave here, it will be impossible to assign them just based on the 1D experiment. Then you will have to move on to 2D, that you introduce another dimension to separate those peaks. Here are a list of those 2D NMR experiments that are available. There are two types of 2D NMR experiments, homonuclear and heteronuclear. So in homonuclear experiments, you'll get a spectrum that both of the X and Y dimensions are protons. And the most commonly used are the COSY, TOXY, NOSY, and ROSY experiments. And for heteronuclear experiments, the x-axis of your spectrum will be proton, and the y-axis will be carbon-13. And that is the HSQC and HMBC experiments that are most commonly run to characterize small molecules. And also, the 2D spectrum will look a little bit different from those 1D. Now you have two dimensions. If you view those 2D spectrum in 3 dimensions, you will have those F2 axis, F1 axis, and your peak actually look like those mountains. And it's not very convenient to view those 2D in those 3D dimensions. So we actually use a contour plot for those 2D NMR spectrum. So here you will have, in those 2D NMR spectrum, you have a proton in x-axis. In this example, you have carbon-13 in the y-axis. And then these peaks actually look like contours, and those contour lines actually represent the intensity of those peaks. So from those 2D NMR experiments, in this example, you actually get 2 pieces of information, the proton chemical sheet and the carbon-13 chemical sheet. And in this case, this cross peak indicates a correlation between a proton and another carbon nuclei that is separated by 1 bond. And so we'll move on to those 2D experiments that are available. The first one is COSY. So this is experiments that correlate protons that are 2 to 3 bonds apart. If you have a molecule, you have like these 2 protons, they are 3 bonds apart, and these 2 protons, they are 2 bonds apart away. And in this case, you will see a cross peak in the COSY spectrum, indicating the correlations between those protons. And this is a COSY spectrum of the molecule ethylbenzene. This 2D spectrum, of course, you'll first notice that you have 2 dimensions. You have both proton in the x-axis and proton in the y-axis. And then you will notice there's a diagonal peak. So this diagonal peak divides the spectrum to 2 equal halves. Those 2 equal halves are actually symmetrical to the diagonal. And the peaks we are interested in are those cross peaks, not the diagonal peaks. And we can take those protons 7 and 8 as an example. So from the 1D spectrum, I know that this peak belongs to the methylene proton, and this peak belongs to the methyl group number 8. So in the 2D spectrum, you can actually see a cross peak actually show up here. This cross peak shows that proton 8 is coupled to proton 7 in the COSY spectrum because they are only 2 to 3 bonds apart. And then you also notice the diagonal peak. Those diagonal peaks is just the proton coupled to itself. And then the other cross peak is just showing you that the same information because they are symmetrical to the diagonal, that shows you the 7 is coupled to 8 in the COSY spectrum. So COSY spectrum gives you short range correlations. And if you want to detect some long range correlations, you will run those TOXY experiments. So these experiments correlate protons in the same spin system, and that are up to 5 to 6 bonds away. So for this proton showing here on the very left, I will be able to detect its correlation to those other 3 protons because they are 5 to 6 bonds apart. And this is a toxic spectrum for ethylbenzene. We can zoom into a specific region, like this region. We are looking at the coupling between those aromatic protons to those protons in the methyl and the methylene group. So here I'm showing you this zoom in part, and we can first check those cross peaks that shows proton 3 and 5 on the aromatic ring is coupled to proton 7 and 8. So these are long range coupling. As you see, 7 and 8 is actually quite far away from 3 and 5. But in the toxic spectrum, you can see the correlation peaks. And then looking at 2 and 6, we also see some correlations from the toxic spectrum that shows 2 and 6 are coupled to 7 and 8 as well. And then move on to the next, we see peak number 4 from the aromatic ring is also coupled to 7. And since the methyl proton 8 is quite far away from the aromatic ring proton 4, I did not observe any cross peak for those correlations. So these toxic experiments are good for protons that are 5 to 6 bonds apart. And for the cozy and toxic experiments, they are called through bound correlations. So all of those correlations you detected, they are actually detected through J coupling. And there are another type of experiments that is called NOSY and ROSY that actually give you through space correlation. So these 2 protons does not have to be J coupled. As long as they are closing space, you will observe a correlation peak. So this kind of experiments correlates all protons which are closing space. Generally speaking, if they are within 5 angstrom, you will be able to see a cross peak in those experiments. And we call this cross peak in those experiments, we call this cross peak called an NOE peak. And as I said here, there are 2 types of experiments for space correlation, that is NOSY and ROSY. They are actually can be used in different conditions. NOSY works well for molecules of very low and very high molecular weight, while ROSY works well for molecules with intermediate molecular weight, usually around 1,000 to 2,000 grams per mole. And this is actually because the percentage of NOE, or here you can view it as the intensity of your cross peak in your NOSY spectrum, it will actually depends on the molecular weight of the sample. If you have a small molecular weight sample, and NOE will be positive, and while if you have a large molecular weight sample, NOE will be negative. However, if you have an intermediate molecular weight sample, NOE will be 0, indicating you will not observe any peak in your AMR spectrum. While for those ROE or the ROSY spectrum, ROE will always be positive, so you'll always see a peak in your ROSY spectrum. So that is why when you have intermediate molecular weight sample, use the ROSY experiments. While you have lower or higher molecular weight sample, NOSY experiments is actually can work very well. Those kind of through space correlations can actually be very helpful, especially in the condition you want to identify and differentiate between different isomers. Here in this example I gave, this is a NOSY spectrum that can be used to differentiate between those 2 anomers. So for those alpha anomer, in the NOSY spectrum, you will see a cross peak indicates a correlation, NOE correlation between the proton 1 and proton 2. While if you have a beta anomer for this type of molecule, then you will not see the same proton 1, proton 2 correlation. Instead, you see proton 1 is correlated to proton 5, and proton 1 is also correlated to proton 3. So these are actually helpful in these kinds of situations. For those 2D experiments, COSY, TOXY, NOSY, and ROSY, they can actually be run in a 1D version. So this is called selective 1D experiments. In this kind of experiments, instead of running a 2D experiment that can take a very long time, maybe half an hour to an hour, you can run a selectively 1D experiment. Well, each of those 1D can just take a few minutes. This kind of experiment can be especially useful if you have low sample concentration, or if you have a mixture sample, there are a lot of overlap peaks, or you are only interested in a few correlations. And here is an example for the selective 1D toxicity. As you see now, I just run all of those as a 1D instead of 2D. First, I just run a normal 1D NMR spectrum. And in this spectrum, I can assign all of those peaks from the aromatic ring and from the methylene and methyl protons. And then say if I want to know if which peak is correlated to 3 and 5 in the toxic spectrum, so then I just run a experiment called selective 1D toxicity. In this experiment, I selectively excite the peak I'm interested in. Here I excite 3 and 5. And then in this 1D toxic spectrum, I see that peak 2, 6, and 4 showed up. So indicating 2, 6, and 4 is correlated to 3 and 5 in this 1D. And this experiment I run is just like 1 minute. I think if I increase the number of scans a little bit more, I might see the correlation, another correlation peak show up here from 7 correlated 3 and 5. So you can do this 1D toxicity for other peak as well. If you are interested in the methyl group correlation, then you selectively excite this methyl proton 8. And then in the 1D toxic spectrum, the peak from the methylene proton 7 show up, indicating these two are correlated. And also you can selectively excite 7, and then peak 8 showed up, indicating they are correlated. So this actually is very time efficient. So all of those three together took me 3 minutes, and then it gave me some very useful information. And moving on to those heteronuclear experiments, the first one is also most commonly used one is HSQC. So it's proton carbon 13 correlated HSQC. And so in this kind of experiments, a peak exists when the proton is directly bound to the carbon. Then this provides additional resolution because now you separate the peak in both the proton and the carbon 13 dimension. And this is an example of the proton carbon 13 HSQC. We will take those aromatic ring region as an example. Each of the cross peak indicates the proton is coupled to its directly attached carbon. So here you see that 3 and 5 is now coupled to its directly attached proton is coupled to its directly attached carbon. Same for 2 and 6, and same for 4. This is for direct one bond correlation. And if you want to observe long range correlation, you can, there's another one here. For those HSQC I showed you, this is just a normal HSQC. As you see, all those peaks are positive. And you can actually run a special HSQC called multiplicity edited HSQC. And it will provide you similar information as the carbon 13 depth experiment I mentioned before. So now if you run one, all the CH2 peak will be negative, and other CH and CH3 peak will be positive. As you see here, the number 7, which is the CH2 group, now it showed a negative peak. So this will also be helpful. Okay, so if you want to detect the long range coupling, you can then run another experiment called HMBC. Instead of one bond direct coupling, this one will show you coupling that are 2 to 3 bonds away. In this case, I will be able to see this proton is coupled to those other 3 carbons in the HMBC spectrum. As you see here, this is the HMBC spectrum for ethylbenzene, and we can take 7 as an example. So 7 is a proton. It's coupled to carbon 8 and carbon 2 and 6, and also carbon 1. So this shows you more correlation information. And those 2D experiments, as I mentioned, they kind of take longer time. For those COSY HMBC HSQC, they can take 30 minutes to 1 hour. Nosy and toxic might be a little bit longer, 1 to 1.5 hours. If you run each of them in total, they will take you a few hours. And nowadays, we have those modern NMR experiments. This one is called NOVA, available. So this one actually combines all of those 2D experiments into one. And instead of running a few hours to the experiments, now all of them will just take 27 minutes. And this is a very useful experiment to try. We also have those available on ICON-NMR. And showing you here is that in this 27-minute NOVA, we got an HMQC, HSQC, COSY, and NOSY spectrum. And each of them just took 6 minutes. So it's very time efficient. Now we can move on to setting up those experiments on ICON-NMR. Similar to the 1D experiments, all of those 2D experiments are set up in ICON-NMR already. So you can just select the experiments that you are interested in. We have COSY, Toxic, NOSY, ROSY, HSQC, HMBC. We also have those selective 1D Toxic, NOSY experiments available. And finally, NOVA is also available under ICON-NMR. And when setting up those 2D experiments, a little bit different from the 1D is that you may want to pay attention to this TD value. Now in 2D experiments, those TD can be important as they determine the resolution. For generally speaking, those values are already set and it's good for most of the sample. In the case you want to increase the resolution, you can increase those TD value to like 400 or 512 for different 2D experiments. This is for those COSY experiments setup. Those O1P, O2P, 1SW, 2SW can also be changed as similar to those 1D experiments. And those 1TD is the one you may want to change. So you can first run a TD with 256, see if you are happy with the resolution. And then you can try to increase the resolution a little bit and see if you improve your spectrum. The toxic experiment has a very important parameter called toxic mixing time. In this experiment, it's called D9. This value generally it is set to 60 to 120 milliseconds. The default value we give is 80 milliseconds. The larger the mixing time, the more protons will be correlated. One way to test if your mixing time is good is to just run a series of toxic experiments with different mixing time. You can start with 60 milliseconds and slowly increase the toxic mixing time. And then in your spectrum, you can see if you observe more peaks in your toxic spectra. So generally 80 milliseconds is good for most of your sample. And NOSY spectrum also has a mixing time parameter called D8. And this parameter actually also depends on the molecular weight. For small molecules, 500 milliseconds to 1 second is good. Medium-sized molecule, you can set it to 100 milliseconds to 500 milliseconds. And for larger molecules, you will set to smaller mixing time, 50 milliseconds to 200 milliseconds. Also, similar to the toxic experiment, the larger the mixing time, the more NOE will be observed in your NOSY spectrum. And in ROSY spectrum, this one also has a mixing time. This one, the parameter is called P15. You can set that to 300 to 600 milliseconds for small molecule, and then 200 to 300 milliseconds for intermediate weight. This one, the default one is now set to 200 milliseconds. And there's no special parameters that you need to pay attention in the HSQC spectrum. Probably change the O1P or SW as needed, or the size of FID, the TD, if you want more resolution. But there's no mixing time, this kind of parameters for HSQC. And same for the multiplicity edited HSQC. There's no special parameters for this experiment. And then in the HMBC experiment, there's actually a very important parameter. That's the constant 13. This is a long-range J coupling constant for HMBC. This value is set to 8 to cover most of those J coupling constants, but you can actually increase or decrease this value depending on your sample J coupling constant. Here, this table just gave you the common J coupling constant for different types of carbon and proton. You see most of those values are less than 15, but if you have unsaturated carbon and proton, these values may go to like 20 or 40. So if you want to observe very small J coupling in HMBC, you can decrease the constant 13 to values like 3, or you can, if you want to observe a larger J coupling constant, then you can increase that value to like 15. But generally 8 is good for most of your sample. And also HMBC has less sensitivity than HSQC, so it will take longer time. You can first look at your HSQC. If you get a very good data on HSQC by 2 scans, then maybe set your number of scans of HMBC to 8. So then you will have a very good data in HMBC. And this one is the parameters for NOVA. Since this one, for this specific example I gave you here called BSCN, it can run HMBC, HSQC, COSY, and NOSY in just one experiment. So this one contains all the important parameters for those experiments. So it contains the NOSY mixing time, and then the constant 13 for the HMBC J coupling. And also you can check the number of scans and say if you want to increase the number of scans to increase the sensitivity. And for the selective 1D experiments, the example I gave here is 1D Toxy and NOSY. They are actually similar to the 2D experiments that you need to define the Toxy mixing time, and similar for the NOSY. You also need to detect the, you want to define the mixing time. So the experiment I want to actually show you is to setting up those Toxy experiments. So this is the only experiment that needs to be set up manually. So from here, we can actually move on to ICON-NMR, and I will show you how to set up those experiments. So I'll first log into the 600 NMR computer. Okay, so now I hope everybody can see the ICON-NMR screen now. So this is a software that we use to control the spectrometer on the 600 megahertz in Marysville Coleman Hall. So when you log in, you will see that there are the holder number here. So just to pick up the holder that you put your sample in, and you just double click, and now you will ask you to give a name for the experiment you want to run. So you can give any name, like a test or workshop. And then you will just automatically assign a number to your experiment. So this number can be any number. You can change that to 1 or 2, and the default is set to 10. And then you will need to select the solvent. And in my case, it's chloroform. So we have a list of solvents here available, and you can just pick up any solvent for your sample. And now you will go to experiment and click the down arrow here. And that's the experiment I mentioned that is available to you. So we have those different proton experiments and carbon experiments and all those 2D experiments down here. And so just to select any one that you want to run. As an example here, I will just show you, I will pick up a carbon 13 experiment. And then the other parameters, the other icon here doesn't really matter. The only one I want to show you is this called PAR here. So if you click on it, it shows edit specific parameter. So that's the table I showed you. So this is a list of parameters that you can change. And any values like O1P, 1SW, number of scans, you can change those values. And if you're happy with the values, then you click on OK. And now the experiment is set and it's ready to go. So once you are happy with that, click on the experiment and click on submit. And then the experiments will automatically run, and then you will get the data by email. So it's very, very convenient. And if you have new experiments that is not available here, let us know. We can set it up, add to your account, and then you can run it under your own account. So this is for running those very normal 1D and 2D AMR experiments. And if we want to run those selective 1D AMR experiments, like the one I mentioned today, the selective 1D toxi, can actually go here and select the one we want to run. So for the toxic experiment, it's actually at the very bottom. And the one I want to select is this selective toxic experiment. You can also select other ones like selective cozy, nosy, and rosy. So if I select this one, it automatically opens on 2 experiments. So the first one, as you see around, is actually the normal 1D proton. And then in this 1D proton, you will need to define the peak you want to excite. And once that peak is defined and saved, you can run the second one. That's the selected experiment you want to run. So if you do submit, there will be a pop-up window show up. It will show you have selected a selected experiment. So you want to define a region, and then you can click on OK. Once you click on OK, the experiment will get run. So now it's queued. If I start the ICON-NMR, this experiment will get run, and then you will run those 1D protons. You will be able to see these 1D protons. As an example here, before the workshop, I just run a 1D selective AMR experiment. I set it up as the way I just showed you, and it was run and finished. So now this 1D proton experiment on my sample is finished. But the 1D toxic experiment has not started yet because it's waiting for me to define the region that I'm interested in. So I will go to those proton experiments, which I just run. So I can just go here. This is experiment I run for those 1D protons. I double click that experiment, then it will guide me go to this another software called TopSpin. So this software is actually the software that can manually control the spectrometer. So now this is the spectrum I just collected. This is a 1D proton spectrum for the ethylbenzene sample. As you see, the ICON-NMR actually automatically did peak picking and integration for me. So what I need to do is to define the region that I am interested in. So I will go to Acquire, and then go to More. And here in the down window, I can check this Setup Selected 1D Experiment. And I'll click on that. Now it showed me that I can set up those experiments, but I need to define the region. So I'll go to Define Region, and then it opened up this to let me define the region. And the first thing I do is that I deselect this Define Region icon. I just need to first delete all the integrations that ICON-NMR already did it for me automatically. So I just go to this integration, and I right click, and I just set a delete current integration. So I can delete all of them. And there's another way you can just delete all of them at once. So here I will delete them one by one. And now there's no integration anymore. And then I can define the region I want to excite. This kind of experiment allows you to define as many regions as possible. So we can first go to enlarge into this region, and then I click on this define region icon, and then drag my mouse, and then now this region is added, and then I know that this will automatically log me out in 2 minutes. So I can go back, And I know this peak is a chloroform peak. So the first peak I want to excite is those aromatic rings 3 and 5. And then maybe I will excite this whole region. And then I will deselect and go to the full spectrum. And then I'll enlarge to that. And I'll define this region. Go to the full spectrum. And I go to those methyl group. And I'll define this region again. So now if I go to the full spectrum, you see there are 4 integrations shows up. So I define 4 regions. Now I can go to this save and export region, and I'll say I'll save region to REG. So I'll click on that, and then maybe I want to save this region that to the spectrum again. So I will just click on return save region. Okay, so now this integration and this region I defined here are those 4 that I'm interested in. Now those regions are defined, then I can go back to the ICON-NMR, and I want to log in again. And here is where I will enter the information for my 1D selective tox experiment. As I mentioned, we just defined 4 regions, so I want to run 4 tox experiments. So I will need to go here, and we need to add another experiment. We need to add a total of 4. So now 1, 2, 3, 4. And also for each of them, I will select the selective tox experiments. Same for the second one. So these are the 4 selective experiments. And as you see, it automatically uses the first proton experiment as a reference. So now those 4 will correspond to those 4 regions that I just selected. And now I can even go to those edit specific parameters and see if I want to increase the number of scans. And once I'm happy with that, I will just click on submit. And I'll start the queue. And now you see that ICON-NMR is actually automatically running my experiments. This one, you run that one first. So what it will do is it will load your sample to our magnet, automatically do tuning matching and rotation, lock, shim, acquire process. So everything is automatic. And once that is done, you will see a check mark for all of them. And then when setting up an account for you, will enter your email address. And so all the data will be processed and emailed to you automatically. So once I set up those experiments, I'll just leave and do my other stuff. And then I check my email and then, okay, my experiment's done, and I can check the data. So this is a very convenient software to do automatic experiments. Okay, so that's the demonstration for the 1D tox experiments, and also some demonstration for the 1D and 2D AMR experiments we just mentioned before. Okay, I'll go back to the slides. And the one we just ended up is over here. These are just some images that showing you how to set up those 1D tox experiments. And finally, this is a summary for the workflow for structural elucidation for small molecules. You will need to first run a 1D proton, a 1D carbon, and then if the proton carbon look good, you directly go to the 2D experiments. Start with HSQC first. That one has very high sensitivity, and it will give you the proton and carbon correlation. And that will help you at least to know if your molecule has a correct structure. And once that is done, go to COSY. COSY also has very high sensitivity and will give you short range proton-proton correlation. And generally, after you get COSY and HSQC, if you have a relatively small molecule, you can assign most of the peak. If not, go to HMBC and TOXI to identify more peak correlation. And if you have other through space correlation you want to know, then run those 2D NOSI and 2D ROSI data. And at the same time, you can also select to run those 1D selective experiments or run those some suppression experiments as needed. And I also want to let you know that there are some online training resources available that give very practical NMR training. One is from Bruker that since 2020 and 2021, they gave a lot of training on NMR. You can actually go to those links, and those videos are still available, so you can watch those videos when you have time. And also, MNOVA provides some free training sessions that are available on their website, and I've listed the link here. Okay, so we are done with the experiment introduction. So we still have some time, so I will go ahead and show you how to process data using MNOVA. So first to start my MNOVA software. I think most of you have downloaded MNOVA and you have the license available. If not, let me know. I will send you the link for the license. MNOVA is a very powerful tool for small molecule characterization. And with that software, you can do almost all those analysis and processing. So I'm waiting for the software to start. And I will show you how to process and analyze those 1D and 2D data. And this is MNOVA software. The version I use is 12.0.4. You may have newer or older version, but the layout will be similar and the functions are all very similar. When I open MNOVA, the first thing I do is to go to File and click on Preference. And then in Preference, I'll go to NMR, Import, and I'll make sure I check the parameters for apodization, zero filling, and linear prediction. I'll make sure those three are checked. This means that you will import those parameters from your raw data. And when we set up those experiments for you on TOPSing, all those parameters are optimized. So if you just directly import those data, import those from your data, then you don't need to worry about those parameters when using MNOVA to process the data. And also you can go to drawing tools. And in drawing tools, you can change the resolution of the image that you want to export. This is helpful if you want to set up a very high resolution image for publication. So you can change the resolution and quality. And once you are happy with that, click on OK. And then now you can open the spectrum you want to analyze. There are several ways to open it. If you go to Open, and then you just go to the spectrum that you are interested in, you can either open them one by one or just directly drag those whole folder into MNOVA and it will automatically open it. If you want to open them one by one, then for the 1D data, you will click on this FID and it will open it. And then for the 2D data, you will need to open this one called SER, and then MNOVA will automatically open the spectrum. And since I'm interested in all of them, I just drag those into those window, and you see now it's opening all the files to me. Okay, so now we have for spectrum, I have a 1D proton and a 1D carbon, this one, and I think this one is HSQC and COSY. So I'll show you how to analyze those spectrum. So first we'll go to the 1D proton. And First thing you may want to do is to change the properties of your spectrum. If you right click and then go to properties, there are a lot of properties you can actually change. You can change the background color. You can ask it to increase the title or not. So if we do apply here, and if you have a title, those titles are actually stored in your raw data, and it will show up if you check this title. And if not, and we apply, those titles will disappear. And you can add grid. You can see, you can add horizontal or vertical grid for your spectrum. And another way is just not selected. And you can go to those 1D. And here you can change the color of your spectrum. You can change it to other color like red. And you can change the line width of your spectrum. The other useful one is to go to this horizontal one. Here you can change the label of your spectrum. If it's a proton experiment, you can do 1H. If it's a carbon-13, change that to carbon-13. And vertical, you can change it as well. If you check vertical, it will show the intensity label for those 1D NMR experiments. So those are the ones that I find useful for the 1D data. And then we can go to processing. First, to process the spectrum. And the first thing we do is to actually check the phase of the spectrum. As I mentioned to you before, apodization, zero filling, those parameters were already imported from the raw data. So most of the time, you don't need to check those apodization, zero filling. And for 1D NMR experiments, so you can go to those phase correction. So MNOVA can do manual correction, so or auto correction for you. So we will do auto correction first for those 1D protons, and then in the carbon-13 spectrum, I'll show you how to do it manually. So if you click on auto phase correction and automatic, then the spectrum is automatically phased. There's not much difference because the peak is already very good. It's positive before the phase correction. And then I will do automatic baseline correction. So you can scroll your wheels and then you can check the baseline of your spectrum. Now the baseline is not completely flat. So what I do is to do baseline correction, automatic baseline correction, and then click on baseline correction. And the one I want to choose is actually this Burson polynomial fit. This is the default one that MNOVA recommends. So I just choose this one and click on OK. So the baseline looks much better. However, on the edges, you still see those curves. These are not from your sample, but it's from some instrument artifacts. So we can actually fix these by go to the more processing. And if you go to group delay and do an enhanced correction and click on OK, so now my baseline looks much better. So those curves are gone and it's flat. Now I'm happy with the baseline and phase correction. And then we can go to analysis. So the first step for analysis is to do reference. So you can either reference the TMS peak or you can reference to your solvent peak. This, I'm going to show you how to do indirect referencing for the X nuclei. So I will reference the TMS peak to the 0 ppm position. So I'll go to reference, and then I go to the TMS peak, and the MNOVA software will automatically recognize the peak, and then I'll just left click, and I give a new shift for it. So it's already 0, and you can add annotation saying it's TMS, or you can go to solvents, and there's a list of solvents available, and then you can select TMS, and OK. So now it shows this one is TMS and the peak is referenced. And then the next step is to do peak peaking as shown on MNOVA. You can do auto peak peaking or manual. You can also do manual threshold peak peaking or peak by peak. So for proton, I'll just do an auto peak peaking. So now it's automatically picked all the peaks, and you can click on this to zoom in and check how those peaks look like. You see it also automatically detected the chloroform peak. If you want to go to the full spectrum, click this full spectrum, And then we go back to this region. And this is the methylene protons, the methyl protons. And so all the proton peaks are picked. And you can also check those tables, NMR peak tables. That will give you a list of those peaks and also showing you if they are chloroform or not. If you are happy with those peaks, that's fine. If not, you can actually delete some of those peaks. Like here, I can just right click. I select the peak I want to delete, and right click, and I can see I want to delete this peak. So now that peak will gone, and then go to this region and make sure we did not pick extra peak in that region. And that's the water peak, so that doesn't matter. So now I'm happy with the peak picking, and then we can do integration. Again, MNOVA can do auto integration, or you can do the manual integration. If you do auto integration, click on auto integration, it automatically detected all those peaks that you might be interested in. And you see that integration is done. And if you want to do the manual integration, we can select delete all integration. And then we go to the region we want to do integration first. And select those manual. And then you just select the peak you want to do integration. No peak. Click on manual again. And that's how you do the manual integration. And you can edit the integration value. If you go to that specific integration, right click, edit integral, and you can normalize that to the number you want to normalize. So I want to normalize to 3 and enter. So now that integration part is done. Okay, so once the integration is done, we can do multiplicity analysis. And this part you can, maybe the best way is to first do it automatically. And then you check those multiplicity one by one and see if you're happy with the automation. And here it automatically did the multiplicity analysis. And then we can go ahead and check those. And it did this analysis for this peak and that peak. And then if you go to the multiplicity table, you will see that it also reports the multiplicity and also those J coupling constants for different protons. And then it has a multiplicity report over here that you can actually report. Another important feature is that if you go to setup report, you can actually select the journal that you want to report, because different journals have different requirements for those reports. So you can select the journal that you are interested in, and they will generate the multiplicity report for you. And if you are happy with the multiplicity, you can just click on report. And those multiplicity report will show up over here for your specific molecule. And another useful feature is we can copy this multiplicity, copy it. This will be useful if you are reading a literature and those multiplicity report, there are also some report in the literature. So you can copy their multiplicity, and then you go to tools and low script and NMR tools. So there is a multiplicity report to spectrum. And then you can paste the report onto it and then click on OK. And then MNOVA will actually generate a spectrum for you based on the multiplicity report. So that's very useful if you want to visualize the spectrum in your literature. And it can also do peak table to spectrum. So if you have a peak table, you can copy that into MNOVA and it will generate a spectrum for you based on the peak prediction. Yeah, now let's go back to that proton spectrum. And so we did multiplicity analysis integration. And then other thing that is very useful is if you go to view and click on these parameters, check that one. So it will show you a list of parameters for your experiment. Sometimes users ask me, how do I find those important parameters? Because you want to write a material and method part, you want to mention the temperature you run the experiments, the pulse program, and also some other important parameters like relaxation delay, number of scans, and so on. So all of these actually you can get it by just click on the parameters. And you see it gives you the solvent information, the instrument information, even have the probe information available. And if you go to customize, you can check the ones you want to report. And also you can add some parameters that you are interested in. So we can then report the parameters. So this table will report over here, and it will give you all the important parameters. Now we can adjust the spectrum a little bit and move the table to the right. Right, so that is the parameters that you can include in material and methods. So that's for proton spectrum analysis. And then for carbon-13, we'll go to those carbon-13 experiments first. Also, we'll do processing first. This time I'll show you how to do manual phase correction, because right now these phases are not correct. So the first thing I do is click on manual correction. And this window shows you how to do manual correction. I will first set up the pivot point. The pivot point will be set to the peak, like the first peak on your left edge or the first peak on the right edge. In this case, I will set it up to the peak at 144 p.m. So I just move this arrow here, and then that blue line will then align with my peak. And I'll set that to the pivot point. And then I'll just enlarge to this region because I'm interested in this pivot point first. I'll move just on my peak. Okay, so now this pivot point is aligned with my peak of interest. And then I'll first change the zero order phase, that's pH 0. And MNOVA showed you that you can click on the left button and then drag your mouse. Then you should be able to change the pH 0 value. And once you change that pH 0 value, you will see your peak becomes positive. So what I do is to left click and drag. And now you see this peak is now completely positive. I change it a little bit more. That peak is positive. And so this peak at the very left edge is positive. However, now if you check the whole spectrum, those other peaks are still not completely positive. So what you do is then to change pH 1. So if you want to change pH 1, you will click the right button and then drag your mouse. And then check if the other peaks change, the phase of the other peak change. So now I'm right click and now all of those peaks are positive. So the phase of the pivot point will not change if you change the first order phase. So that is why I'll do the zero order first, make sure the pivot point peak is completely positive, and then I do the first order phase correction. Now I'm happy with the phase. I can close the window and go to the full spectrum, and then we can do baseline correction. For those carbon-13 experiments, those Burson polynomial fit does not work quite well. So I will use those Whittaker smoother baseline correction, which is more aggressive. So I'll choose that one, click on OK, and that will make the baseline completely flat. So I'm done with the processing for the carbon-13 experiments. Now we go to analysis, and then we can do reference. So this time I'll do indirect referencing. So I go to reference and click on absolute reference. So in here, you can actually select the experiment you want to reference, and it's actually referenced to your proton TMS peak. And I'll just do the referencing for all of the other spectrum, including the COSY, HSQC, and carbon-13 NMR experiments. And then I will click on OK. And now it's done. So all of my spectrum, the 2D data, and also this 1D carbon are indirectly referenced to my 1D proton spectrum. So that's done with the reference. And we can do peak picking. If we do it manually, I like to do peak by peak. So I click on that and I go to each peak and then left click. And then MNOVA will automatically show those chemical shifts of those peaks. And once that is done, there's really no need for multiplicity analysis or integration for carbon-13. So this is for carbon-13 processing. Now we can go to those 2D data. So this one is HSQC, and the next one is a COSY experiment. Looking at the 2D data, the first thing I want to change is this label on the y-axis. I will go to properties. I'll change that to carbon-13. Let's go to scale, and on verticals, I change that to carbon-13 and click on OK. And you can also change other properties. For example, if I go to this specific part, I go to properties and 2D traces. So here you can change the color of your contours. You can choose different color. And also you can change the scaling. Sometimes if I want to make a very nice image for publication, changing the scaling can change the contour lines. If you increase the scaling, apply, you see there will be less contour lines. And if you decrease the scaling number, and there will be more contour lines. And also you can change the line width of those contour lines here. And the 2D experiments, I will also go to processing first. First, I will make sure that the X and Y axis traces are the ones that I just referenced to. So those proton experiments, I'll drag it into the X axis. And then the carbon-13 experiments, I'll drag it to the Y axis. So now those proton and the carbon axis are the real AMR spectrum I just draw. And then we can go to processing. As I said, apodization and zero filling we already imported from the your raw data. But if you want to look at it for 2D AMR, it might be important. These are already imported. So we actually apply different window function to your spectrum to make the line shape and the resolution much better. Like for those HSQC spectrum, we are applying those sine square window functions for along both F1 and F2 dimension. And for the zero fillings, we actually add zeros to your data. So if you go to, this is actually along F2. And if you go to the F1 dimension, click on zero filling, and you'll see that your original data points is 256, and we actually add more data points to 1024 to increase, to make the line shape much better. So these are all looks very good. And for the phase correction, we can just do it auto phase correction, automatic, and then we do an auto baseline correction. And this time I'll just choose the default one and the Burson polynomial feed, and I'll apply to all dimensions, both on the X and Y axis, and click on OK. So now this is the spectrum for the HSQC. And for those analysis part, reference, we are already done. We can do peak picking. Take this as an example. For those 2D data, if you go to this specific peak you want to pick, MNOVA will also automatically identify the peak position. So if you left click, and now it will show you the peak position. So it will start with the x-axis chemical shift and then the y-axis chemical shift. So you can pick all of those peaks, and of course those will also show up in the peak table that you can edit. You can also do those automatically. Now you have those peaks, and that's for the 2D code HSQC. And similar for those CODI data, you can do the same processing. And because of how this CODI data is collected, you will not be able to do phase correction. So the only thing you need to do is just do baseline correction. I will apply to all dimensions. And then analysis, similarly, you can peak, and then you can look at your data and see if you've got any important correlation peaks. And for assignments, if you want to actually assign the structure of your molecule, usually I will just draw the structure in ChemDraw first. So now I'll just say, from ChemDraw, I'll just copy a structure into this window, and now this is a structure that I'm interested in, and then you can do assignments using MNOVA. So what you do is to go to assignments. There are auto assign or manual assign, and I prefer to do it manually. Even though you do auto assignments, you still have to check the assignments one by one. If you do manual assign, and first we go to those this peak at 1.24 ppm, and if you left click that peak, and then you left click the proton that you want to assign, now this will turn to green. So number 8 is assigned to this peak. And we can also do the same for the other peak, 7 for this, and can do aromatic region assignments. Click on that peak, that will be maybe 2 and 6, and those you can assign all of them. That, and that would be 4. And once your assignment is done, you can actually go to those 2D, and you see that those assignments are also labeled on your 2D data. And so you can also check the correlation on your 2D spectrum one by one. Here, I haven't assigned the carbon 13 yet, but if you assign the carbon as well, these correlations will be very easily identified. So you can see those HSQC will help you to identify the proton carbon 13 correlation. Now I know this peak belongs to 7, this belongs to 8 carbon, and those aromatic ring will also get assigned. So that's some tips on assignments. And once you're happy with the data analysis, you can go to File, and you can save those. You can either save as PDF, MNOVA, or image. So there are a lot of options available here, different types. That's very convenient. Okay, so that's all for the MNOVA processing. I think we have some time left, so I'm open to any questions you may have. I'll go back to the slides. And if you have any questions, I think you can either unmute yourself or you can submit your question to chat. And these slides and also this video will be available after the workshop. I will send you the link, and so you can go back and check those parameters and all those tables I mentioned, and you can watch those videos again to set up the parameters. Okay.